Good evening, everyone, and warmly welcome to Aalto University and to our beautiful main building, Dipoli. My name is Tuija Pulkkinen. I'm the Vice President for Research and Innovations here at Aalto University. And it's my special pleasure to welcome you to this Nobel Laureate lecture on gravitational waves. This event is hosted by the Finnish Physical Society together with Aalto University. So we're co-organizing this event as part of Aalto Festival, which showcases the many talents of Aalto University and advertises itself by collisions, experiments, calculations, disruptions, surprises, and more. And I hope we will hear a bit of all of those also tonight. This co-hosted Nobel lecture in physics is somewhat of a traditional already for us here at Otaniemi campus. Scenarios and teaching projects by our faculty in the What If exhibition at the lobby of this building. But now, without further ado, Rami, please.
Okay. So, many thanks for all of you who have come here. It's a very great pleasure also from the point of view of Finnish Physical Society to welcome you all and to listen to this, which I'm sure will be very, very interesting talk by our guest, Professor Rainer Weiss from the Massachusetts Institute of Technology, who is the Nobel Laureate of last year's Nobel Prize. And this story will be about a project which took about 40 years to discover something that was predicted almost 100 years before. And I think this will be a story of such a great achievement that everybody will actually be in awe after this. So without further delay, let me introduce Rainer Weiss. Welcome.
Thank you. Thank you very much. Thank you. Yeah. Well, thank you for having me, and I hope I don't bore you. I can't talk Finnish, so unfortunately I do have to talk English. And I know now that having come to Helsinki for the first time, almost everybody here talks English. I mean, it's very comfortable, but it's very unnerving to have everybody who should be talking Finnish to me not talking, but English to me. Anyway, I'm going to describe this experiment to you a little, and something about a little of the history, also a little bit about the technology, and then the things we've discovered. And I'll try to end by telling you about the field in general. In other words, there's some future that this field has, which might be interesting to you. So since not everybody knows everything, I'm going to have to start in a very primitive way to begin with. And most of you, by the way, the way I'm going to do things, and I hope you can see this on the screen. You see this little pointer that I'm moving around? I hope you can see that. So those who can't, just who can see it? Way in the back. Can you see this pointer? Okay, great. Otherwise, I would use a pointer with a green light in it, but the people who make the television don't like that. So, whoops, what happened here? So anyway, this is our friend Isaac Newton. And he had a very wonderful theory of gravity, which we talk about all the time. And I'm sure that many of you have learned in high school, and some have learned in college. And what he did a very remarkable thing. What he did is he coupled what was on the Earth, and this apocryphal story that he saw the apple falling in the tree, which is maybe right, not so important, but the connection he made. Why? Gravity is so well understood. Why should you want to work on gravity? And the reason he wanted to work on gravity is because it had this little flaw that it didn't quite work for the planet Mercury, but it had bigger flaws for Einstein. The other flaws, it didn't have anything in it that could deal with large velocities. When things move very fast, Newton's theory doesn't work. When things are very massive, Newton's theory doesn't really work. And most important of all, Newton's theory doesn't work in a way that really was very important to Einstein. There was no way that information took time to travel in Newton's theory. For example, I mean, people, when they were thinking, suppose here we are attracted to the sun, and we are moving in our orbit around the sun, and the sun suddenly disappeared. Magically, it disappeared. Now, you would know that with your eyes in about 8 minutes, that the sun is gone. You should also not know it immediately, as though Newton's theory would have had it, that our Earth now suddenly goes off on a tangent, no longer going around the sun, where the sun was. That piece of information also should take 9 minutes or 8 minutes to get to you. And that was something that was fundamentally missing in Newton's theory. So there was no, what we'll call an information function. A news function did not exist in Newton's theory. So here is Einstein's theory. And Einstein's theory, by the way, there's a sort of anachronism here. Einstein wasn't this old when he made up this equation. I couldn't get a better picture, but now I know where to go. And so now this equation is quite a different story entirely. I can't describe the whole equation to you, but I will describe to you what the equation says, okay? And what the equation says is that this object right here, G, that's the geometry of space, the way you measure space, and also the way you measure time. So it's a geometry of space and time together. And that geometry is dependent on the distribution of matter and energy. In other words, space is now distorted, and we'll see a little picture of that in a minute, and time is distorted by the fact that it matters where the energy and the matter is in the universe. And you'll notice there's no more gravitational force. It's gone. It's all going to be, and here's one way to think about it. And this picture, and I hope you can see this pointer because that's rather important now. And so this is, how many of you, I mean, I come from New York, how many of you know what a jungle gym is? Oh, a few of you do, good. That's a thing that kids play in, and it's a nice, have parallel bars, and you have vertical bars, and you have horizontal bars in 2 dimensions. And what this picture is a cut through the jungle gym, 2-dimensional cut. And that's what this whole little area is that you're seeing there. And what's been done to the jungle gym, because it's a figurative jungle gym, you've placed the sun into it. That's the thing, that was the mass and the energy. And you'll notice what it's done. It's distorted space a little bit. These lines are no longer the straight lines they were out here when you're far away from the sun. There's even a little dimple from the Earth. There it is. There's the Earth. And it makes its little dimple right in there. So the Earth and the sun have distorted space, but they've done another thing which this picture doesn't have in it. And that's only because I'm so lazy I didn't draw it in. And that is, there are clocks supposed to be everywhere. Everywhere there's an intersection, there's a clock, and another clock, and so forth. And these clocks have all been synchronized by a way which you have to think about a little bit. You can't just make a photograph and take a picture of all the clocks. Why? Because they'd all read different times. Why? The ones near you get to the light from the clock that's nearest to you gets into your camera sooner than the clock that's further away from you. So they all would look very strange. All the clocks far away from you would look like they're a lot earlier than the ones that are near you, because that light had to start earlier to get to your camera, to get into that shutter. So this is a tricky business, how you decide clocks are the same everywhere. But it's important you learn how to do that. Not that you have to do that now, but you have to keep that in your mind. And Einstein worried about that a lot. So now comes this other thing. It turns out that not only does matter and energy distort space, but it also changes the way clocks keep time. The clocks that are out here, whoops, what happened there? The clocks that are way out here are all keeping the same time as they did far away from this. But when they get closer, and we're going to encounter this when we begin to look at black holes, the clocks run much more slowly. Not much more. They run more slowly when they're near the big masses. So this is something which is absolutely critical to Einstein's theory. Clocks do not keep the same time everywhere. Those that are near masses, they run more slowly than the ones that are far away from them. Okay? Now, how does motion come about in this thing? Well, once you have space distorted in this way, and you have clocks distorted the way they are, what you have to do, and this is what Einstein thought, you take the shortest path in both time and distance. And matter then moves along those paths that are the shortest distances between places. And they're not necessarily straight lines anymore. And that's how the gravitational force looks like it's there. I mean, that's how gravity gets into this picture and makes all the things happen that Newton's theory did too. Now, here's the new thing. The new thing is this news function. That's the gravitational waves themselves. And this will take a little bit of doing. What the gravitational waves do is first of all, the sources of the gravitational waves are accelerated masses, masses that have been accelerated. Very much like in electricity and magnetism, it's the charges that, when they accelerate in electricity and magnetism, that make electromagnetic waves. And it turns out there's a deep analogy between these gravitational wave sources, but they're not every kind of motion. You have to have non-spherically symmetric motion. A completely spherically symmetric thing, like a big balloon, that's getting bigger and then gets smaller again, does not radiate gravitational waves. It has to be something which has no spherical symmetries. In other words, 2 trains hitting each other like that will do it, or 2 objects going around each other in a circle, like orbiting. They will radiate gravitational waves. Now, the kinematics of these waves, that's how they go. They were alleged by Einstein to travel at the speed of light. Now we know they indeed do travel at the speed of light. I'll tell you about that when we get to what we discovered. And it's so good, in fact, that Einstein had guessed right. They travel at the speed of light to part in 10 to the 15. I hope I can use... Let me just ask quickly. If I say a number like 10 to the 2, how many of you know that that's 100? How many are absolutely mystified by that? Don't be shy. Okay, because I'm going to have to use that. There's no way to deal with big numbers and little numbers without the powers of 10. Okay, thank you for that. So, it turns out they propagate at the speed of light, and we now know this for a fact. And I want to show you what they do. They're transverse waves. The waves that you see in that picture, they're either coming at you or they're going away. And here's what they do. And what's in this picture is that I've sprinkled masses all around, and the gravitational wave that you're going to be looking at either goes into that screen or coming out at you. That doesn't matter. And here is where you stand. You're right here where that little red square is. I hope you can see that. And I will now start this thing so it will drive you a little crazy. Okay, I mean, if you get sick, don't keep looking at it. But, and what you see in that picture, I want to point out what are the important features of this gravitational wave. One of the things is that you'll notice that space is stretching in one dimension, let's say this one, when it's contracting in the perpendicular dimension. Yeah, I hope you can see that. Stretch in one direction, 90 degrees to that, it's compressing. On top of that, there's another pattern. So that's one whole idea. The other pattern is the fact that you'll notice that, for example, let me get this pointer working. Let's take these two masses, one that's very far from you over here and one that's very far from you over there. And you'll notice they're moving a lot more than the ones that are close to you. These two, for example. They're hardly moving at all. And what's characteristic in that picture is the same thing that if you had taken a rubber band, you can do this at home if you want. Take a rubber band, have somebody hold it for you a little bit, and make marks on it every 1/4 of a centimeter. And then pull it. And that pattern, when you pull on that rubber band, is exactly that pattern. It's a pattern at any one moment when you're holding the rubber band steady, is a pattern of constant strain. That's a change in length. Let's say the change in distance between this dot and that dot. That distance change divided by their separation. That's the strain. Delta L divided by L. And that is at any one moment in this picture a constant. For one motion it's negative and for another motion it's positive. And that, by the way, is the field quantity, the quantity that you use to make the detection. You'll see this in a minute. So there are two things about this. There is a stretching of space in one dimension, perpendicular to the direction of propagation. There's an expansion and then a contraction in the corresponding 90-degree direction. And it's a pattern of constant strain at any one instant. So the field quantity is the strain. Okay. So now a little history, a little more history. The first people to ever experience this, but indirectly, were Russell Hulse, who was a graduate student for this gentleman, Joe Taylor, who was a professor at that time at the University of Massachusetts. And what they discovered was something really quite dramatic. What they discovered was a system which they could only do with radio. They did it with a radio telescope. And they were listening at the Arecibo dish, that's a big telescope in Puerto Rico, which now has been, well, they're abandoning it partly because of the hurricane, but also because it's expensive to maintain. But anyway, it's a shame. And what they found is a star, which they later knew what it was. It's a star that made a steady beeping noise, brrr, like that. And it did it at about, well, I think 17 times a second. That's what it says right here. And so they didn't see this thing, they just heard it. And they noticed as they watched this star for a while, or listened to it for a while, they found out that sometimes it went a little faster than 17 times a second, and sometimes a little slower. And eventually they made a model of it, and the model was that it was really going around another thing. And so while it's on this part of the orbit, here, let's say, the antenna is over here. And so here is the pulsar. That's the name of that kind of star. It's a neutron star rotating very quickly. And what it does is while it's coming at the detector, it's going a little, you hear the pulses a little faster. That's the Doppler effect. And when it's going away from, this does keep disappearing. And while it's going away from you, it seems to go a little slower. That gave them the signal that they were looking at a pair of stars. A pair of stars they couldn't see, they could only hear. And that was a huge discovery, and they found out that these two stars were going around each other once every 8 hours. And what they did is they measured all sorts of wonderful parameters that Einstein never even had thought of. Einstein never imagined such a system. It's very tight little nuggets of stars. These stars are about the size of Helsinki, 10 kilometers on the side. And they weigh the sun. We're going to run into these again in a few minutes. And so what happens is that these stars were showing you all the effects that Einstein's theory, the high velocities, the effects that nobody expected out of Newton, they were clear. And over in this picture right here is the first evidence for gravitational waves, real evidence for gravitational waves. What this picture is a picture of epoch. So here's 1973 down here, and there's 2000. And this is the length of time it takes for the orbit to complete. In other words, and you'll notice that the orbit is taking less and less time. As epoch progresses, it takes less and less time. So what happens is these guys are falling toward each other. They're getting faster and they're falling toward each other. And what they plotted in this picture is the dots are the data that they took over all that time, and the line that runs without fitting, that went right through all this data, is Einstein's prediction from his theory for what would happen if these two stars were actually radiating gravitational waves away. They're losing energy into gravitational waves. And this was the very first evidence that people had for gravitational waves. Okay, big deal. This was, and that won the Nobel Prize, by the way. So here's a guy, a little bit later, well, about a little earlier, but he kept on going. He's a gentleman who was a professor at the University of Maryland, and he wanted to actually make a device that would measure gravitational waves directly. In other words, and his idea was to exploit that picture that I showed you. Namely, he had a big bar. Here he is, with a big aluminum bar. You can see him working on the bar. He's making little strain gauges he's putting on it to measure the stretching of that bar as a gravitational wave comes through it. And the way he imagined it, the gravitational wave would come through it, stretch the bar, and then it would ring like as though it had been hit by a hammer from a xylophone. No, bang, and it would ring on. And he would measure that with the strain gauges. Here's the big vacuum system that he put the thing into. Now, he had a terrible problem. He actually did discover gravitational waves, he thought. And that was a complicated issue. By 1969, he began to, he had 3 of these. He had one in Chicago, that's the middle of the United States. He had 2 of them in Maryland, which is toward the East Coast. And he was seeing coincident pulses in them that were at the same time in all 3 of those bars. And he published a paper saying, look, I have evidence for gravitational waves. Well, you don't do that lightly. And he did it very seriously, but now science is a wonderful thing. It turns out it's not a terribly hard experiment. And everybody in the world who was interested could repeat that experiment. And they did, and they saw nothing. And that caused a lot of scandal and worries about the man and whether he was lying, a whole bunch of stuff, which was bad publicity for science. But nevertheless, he had, I think, in his heart, he was doing the right thing, but he actually was not measuring gravitational waves. And I'll tell you right now why we now know, because of the history, that he was insensitive by a factor of 1 million. 1 million in amplitude, being able not, he could not have seen a gravitational wave with that instrument. We now know. And so here's the idea that did make, ultimately, the detection. And so I have to walk you through this a little. The idea here is not to have something stretch. The idea, yes, it still stretches, but you don't use the acoustic noise. What you do is you time light. And here the idea is the following. Here's a laser. That doesn't look like a laser, but think of it as a laser. There it is. And this is a beam splitter. This is a device that divides light. When you put light on one side, it reflects, but it also transmits, as you'll see in a minute. And there are these 2 distant mirrors. That's a mirror that is like those distant dots in that picture of the gravitational wave. Here's another one. And right there is a photodetector. And we'll launch this thing right now, so it'll be a little animation. And what you see is the light hitting, doing what I told you. Wherever there's light, there's red. That means there's power in the light. You would see it. But what you're seeing also is the electric field that's in the light that makes the electromagnetic wave. And right now, these paths are exactly equal in time, and no light goes to the photodetector. You see the 2 waves cancel each other. That's specifically done that way. And now, when a gravitational wave comes down on this thing and pulls one a little closer and one a little further away, you'll see that their light does appear at the photodetector. In other words, you've destroyed the wonderful balance that you set up. The gravitational wave has made one arm stretch and shrinked on the other arm. And now that is, in fact, the whole story of the gravitational wave detection that actually succeeded later. It's a fairly simple idea. This, by the way, is called a Michelson Interferometer, this device. So, and now comes the hard part of the story. And that is that this is Kip Thorne, the man who is in this picture. He's a guru of this field. This is about him in the middle 70s. Okay? And he was looking very hard with his group at what might be the largest strain. That's H. That's the symbol for it. And here's that thing I told you what it is. It's the change in length divided by the separation. And the conclusion that he came to with his group was if you were ever going to detect gravitational waves from astrophysical objects, you had to have a strain that was good enough to measure 10 to the minus 21 strain. And most people, when they heard that, they said, this is ridiculous. You can't do a thing like that. And so let me make it a little more real. When we built LIGO, or the detector ultimately that we're thinking about, the arm length was not a little thing. It was 4 kilometers. And still, even with 4 kilometers, you need to measure 4 times 10 to the minus 18 meters. 4 times 10 to the minus 18 meters, and that's smaller than size, 1,000th the size of a proton. You had to measure that much to be able to see the signals that Kip expected. And what does that mean in the end? It means that you had to do several things. And this is where all the time went that he was talking about, the 40 years or 45 years. First of all, one had to make distance measurements that were 10 to the minus 12, a million times smaller than the wavelength of light. That was the very first thing. You had to be able to measure the motions of those mirrors to 10 to the minus 12 of the wavelength of light. But that isn't the only thing. That was actually the easier part. The harder part is the next thing you had to do. You and I, all of us in this room, are shaking by about 10 to the minus 6 meters. Why? Because the oceans are having waves. If you put a seismometer on the floor here, you'll find out this building, even though it's sitting on rock, and I saw some of those rocks, by the way, is shaking by 10 to the minus 6 meters easily, maybe a few times 10 to the minus 6. And you're trying to measure 10 to the minus 18. So you can't use the Earth as to anchor the mirrors on. You have to float them in inertial space somehow. So that was the second part, and that's a hell of a lot harder than the business of using light. So I don't think I'll do this because that takes too much time. So here's the way it was ultimately done. This is the detector that actually made the discovery, and I'll just walk you through a little of it. I told you I'd tell you a little about the technology. I can't avoid that, okay? And so here's what you're familiar with. You're familiar with the laser. You knew about that from the other animation. You're familiar with the beam splitter, and you're familiar with these distant mirrors, that one and that one. And now here's the gravitational wave coming down. You'll notice there are 3 other mirrors in here now that weren't in the other picture. And what are they? They're the tricks that you have to do to get that factor of 10 to the 12. And so one of the tricks is to make the light bounce back. Here, these are partially reflecting mirrors. In other words, these are not complete mirrors. A little bit of light leaks through those mirrors. And so what happens, it causes the light to bounce back and forth maybe 300 times in here. And you make it do it exactly the same thing on this side, so that still, when the light comes back and is reflected from these, it has spent the same time in both the left arm and the right arm. You still have to have that. So no light goes to the photodetector. It's the same idea. You don't want any light at the photodetector because that makes noise. So there's another mirror now. If no light goes to the photodetector, where's the light going? Well, the light all comes back to the laser. That's where it goes. The light, and here you put a special mirror. It's called the power recycling mirror. And what does it do? It's, again, a partially reflecting mirror, which does the following. Here you have to imagine with me with my little arrow. Oops. So here's the light hitting that partial mirror, and some of it will get reflected back to the laser. So this is one path. But then there's the other path. The light went into the system, coming through it and coming back. So there's another beam. There's a beam that's reflected by this, but also the beam that's transmitted by this mirror. And what you do is you cancel them interferometrically. You make it so no light goes back to the laser at all. It all goes back into the interferometer. That's another interferometer. And what that does, it does something really quite special. And by the way, that idea was invented by the German groups who got into this thing. It was also invented by Ron Drever, one of my colleagues, who died fairly recently. And what the idea now is what you start with, let's say, 10 watts in this laser, and you wind up with, because of this resonance that you have, you wind up with something like maybe 500 watts here in this little cavity, and you wind up with, right now we're winding up with maybe tenths of megawatts of light, hundreds of kilowatts of light in these arms. So suddenly you are dealing with something which is dramatic. You have now gotten all that sensitivity because you've increased the amount of electric field that's actually looking at the gravitational wave. So that's how we solved the problem for the first 10 to the 12. I don't think I want to go through this picture. It's just all the other noises that we had to deal with. But I do want to tell you now a little bit about how we did it. And the thing is that we have 2 detectors, one in Washington State, that's in the northwest part of the United States, another detector in the southeastern part of the United States, that's in Louisiana. There is another detector built by the French and the Italians, which is near Pisa, which is right here, and there's a research detector maintained by the Max Planck Society in Hanover, right here. And there are 2 detectors that are now being built. And we'll see as we go along why we want more detectors. It really has to do with finally doing astronomy and astrophysics with this. That's what you need more detectors for. And I'll get to that in a minute. But there's a project in Japan that's building thing, will be ready in about 3 or 4 years. And there's a project in India which is using a spare detector that LIGO had, but the Indians are building the infrastructure for the system. Okay, here's a picture of, and I'll show you a little travel log of the system so you can imagine what this looks like. This is, I haven't started moving yet, but this is, we're looking above at the one in Louisiana. There are trees down there. So here in the first picture is Louisiana. Here's what it looks like in Hanford. It's a deserty. And these tubes are vacuum tubes sitting inside these concrete covers. And the same exact thing in Louisiana. And here's what these tubes look like. They're evacuated almost to the vacuum of space, the outer space. Here are people working on a thing you have probably right in this building, a laser table, and they're ordinary stuff. And here's the control room for the Louisiana detector. And here are people learning how to run the interferometer there. So that's a little travel log. So you can see the kind, it's large physics, there's no doubt. You're talking about big physics. And what happened is sort of, this is a nice picture, which I will show you, and that is that this is sort of the very early evolution of the interferometers. And what these pictures are pictures of frequency, which is on here, the frequency at which you might be looking. So here's 100 hertz. Here's a kilohertz right there. So the human voice extends from about here to right about there. So that's sort of the length of the piano. That's really what it is. And here are the kind of displacement sensitivities we had. For example, here is 10 to the minus, when by time, this is time. Each one of these curves is a little bit later. You can see they're all given in this table over here. And this is all the improvements that were made. The smaller something is in this picture, the better it is to make gravitational wave detections. And ultimately, we got to the point where you could see a line in here, which was the theoretical curve for the detector. That's this dotted line. We didn't quite make it at the very end, but it got there sort of from about 50 hertz on. It was buried in the real performance of the detector. And we saw nothing. We saw a clean nothing. Now, it turns out, why is that so important? It made it so that people began to trust us. That 10 minus 21 wasn't such a crazy number anymore. This is very close to 10 to the minus 21 strain. And we had an instrument that was getting close, and it was performing as we told people it should. And so people began to say, oh, they began to get, especially the funding agencies, began to sort of breathe a sigh of relief. They had taken this terrible gamble with us, and now at least it hadn't paid off yet, but it wasn't totally fraught with complete nonsense, okay? They were worried about that. So a clean non-detection was very important. You had to prove that you could do it. And then we went ahead and improved other parts of the experiment. And the things that made it so we made a detection are things that worked on that other factor of 10 to the 12, the shaking of the mirror. Now, we already done some of that in the early detector. We hung the detector, but now we had to really do it. And so one of the things, here are two ideas that one of them might be useful to you. That's why I bring it up. A standard technique is this is a whole bunch of pendula. They're all in series, and that's how you get the noise. That's how you get rid of the That's how you get rid of the noise. I don't know why this wants to go forward on its own, but it's doing it. So here's some springs, and the ground is attached to here up there. You attach to the ground, and here's the first pendulum. That's one mass, and then there's that mass is hanging from another one. That's the mass hanging from that one. Here's a thing that looks just like a mirror, but it isn't, hanging from that one. And finally, here's that very precious mirror hanging from the very thing. So there are 4 pendula in series. And what does a pendulum do? You try it for yourself at home. I could take my belt off, but that'd be embarrassing for everybody. So here, let me do it by my hand. Let's say this is the top pendulum, and this is the perfect, wonderful mirror. So let's say when I move very, very slowly, and you do this for yourself, you'll notice that when I move it very slowly, they move together. So that you get no isolation at all at very low frequencies. But suppose the ground is moving fast. It turns out this doesn't follow. It looks just like that. This is moving very quickly, but this doesn't move at all, or very, very little. And you do this 4 times, and it gets you somewhere to what you need, but not enough. And I just want to, I'm not going to describe this picture to you, except those of you who are interested and have the problem with microscopy, or have the problem with making very fine measurements in a noisy place like a city, might want to use this. This is something that you can get the drawings from LIGO. What it is an active vibration system. And this is what it is. It's sitting right here. This is a much more complicated thing. But here's that pendulum. So you can see them all 4 things hanging from this thing. And what is this thing? How many of you, when you go on an airplane, use these headphones that listen to the sound outside and turn it upside down, and so you don't hear it in the headphones? Many of you do that. I mean, it's one way to survive on an airplane. It's also a way to survive kids. I mean, you know, a lot of things. And so it turns out that it's exactly the same idea. What's done here is you have, I mean, here's one stage of it. Here's the seismometer right up there. It's a thing that measures motions. And that is sitting on a platform and it's being pushed around by driving systems. And you make it so that there's a servo system, a control system that makes it so that the seismometer gets no signal at all. In other words, you're pushing the platform to make the seismometer get no motion. And the seismometer is a device that is the thing that senses the motion. So it's a negative feedback system. And what it does is, so you do this twice, and this gets rid of the low frequencies. You can see there's another seismometer. Well, there are two seismometers. It's a little hard to find in this picture. That's called an active vibration isolation system. And boy, if you are doing precision microscopy and you're trouble, the building is shaking, you might be interested in this. Okay? It's a very nice idea. And, okay, so what came of it, yeah, this is jumping on me, so okay, well, we'll just have to live with it. So here's what we discovered when we built this and we started that instrument, the new instrument with these things in it. We saw these two waveforms. What are these waveforms? This is time, and this is strain. And you can see here is 10 to the minus 21 right there. So, you know, Kip wasn't completely crazy. And this is all junk. That's junk. This is in Livingston. But then you'll notice something sort of getting coherent in here. And here is pretty good. And here is the signal at the same time, a little bit later, about 7,000th of a second later, and we'll see that in a second. And again, this stuff is, well, junk. And there's junk over here, but this is pretty coherent. And now let's put them on top of each other. And yes, remember there's noise, but here are the two signals. One slid with respect to the other by about 7,000th of a second. And here they are pretty much on top, but they're not exactly the same because there's noise in both instruments. And that was the big discovery. That was the discovery made in September of 2015. We didn't publish it until February of 2016 because we worried about it being real. We worried a lot about that. Why? Because of Weber's experiences. That's why I told you about Weber. That was a pall that was over us that we had to worry about. So here I'm going to give you another way to look at or hear these signals. And this is a different way of representing them. This is, again, time in this axis here, same length of time. But now, here's the waveform we were talking about in time, the ones you saw already there in Hanford and Livingston. But now we're going to represent to you what the sound is that's associated with these waveforms. And so let me just, and this is frequencies. And here, for example, God damn it. Yeah, here's the 30 hertz, sort of the bottom of the piano is about there. And this is middle C on the piano right there. 256 is definitely middle C. And this thing you're going to see over here is the spectrum of that waveform. So let's see. If this works, you'll hear it. I don't know if you heard that. You heard a bump at the end. Well, let's try to make it a little more audible for you. Here's cheating. This is cheating. Okay. That's the chirp that everybody talks about. And what this is that signal has in it frequency components that run sort of like a glissando on the piano. You make a glissando on the piano, that's what you're going to get, just that. Okay? And the natural system that does that, well, we'll talk about in a minute. Here it is. And this is actually another miracle in this whole business, is that just as the detectors were getting sensitive enough to make detections, people who were doing numerical solutions of the Einstein equations were able to succeed, finally, to get the solutions to the Einstein equations numerically. They were not able to get them analytically at this very critical moment when you'll see in a minute when these two objects get to be moving at the velocity, damn near the velocity of light. And so what was this? And this is not a artist's drawing. This is a computer output of the thing that best fits the data that we have. So let me get it started. What you're seeing here is two black holes. And again, it's that jungle gym cut that has been made that I showed you with the sun in it. There is that jungle gym below this. And now the colors tell you what the time is doing. Where the time, when it's blue and green, the time is okay. But when it's red and black, black says the time has stopped. Okay? And here it is now. What you notice, these little arrows in here, they are the tensions, the stresses or the strains that are in the space. as this thing goes along. On the top corner here, you'll see this sort of time. This will slow down in a second. These two black holes are getting closer and closer. They're moving close to 0.5 the velocity of light in that orbit. I mean, these are stars moving 30 solar masses. And now you can look down into what's going on here. This is a distortion of space, which is unbelievable. Man has never experienced anything like this. And now what's happening is a new black hole is being formed out of the two black holes that have collided. And now you'll see everything gets quiet. And now you see the gravitational waves taking off, and they're heading toward us. And this all happened 1 billion years ago. 1 billion years ago, a distance that 1 billion years away in light times. That was the explanation of what we saw. Interesting thing, after we made the press conference in New York, in Washington, I was in New York giving a lecture at the American Natural History Museum for kids. And I was sitting in the subway, and I noticed, this is now only 2 months after the public got wind of this big discovery. And here's what I saw on the subway. It's this thing right here. Scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet. Okay? And right away, within about another couple of weeks after that, the New Yorker magazine, which is a cartoon but fairly serious magazine otherwise, says, this is one bird talking to the other guy, says, was that you I heard just now? Or was it two black holes colliding? So it was sort of a miracle that this piece of science suddenly appeared in the public conscience. And I've often wondered, especially, I do a lot of talking to high schools and things like that. I was wondering how it, and grade school, why is it? Well, when you talk to a high school class or even a grade school, you ask them, who's a scientist? They all mention Einstein. And it's like Einstein is part of the natural culture. And all of them know about black holes. Why? Because the comic books have black holes in them. They're the most horrible thing that you can encounter. So they knew everything about black holes. So with no problem explaining black holes. So there we are. So anyway, here are the other black holes that we've seen. More. This is the first one we were just talking about. Here is then this is another black hole. This one was somewhat dubious. These all have different masses. You can see what they are over here. Now, the one we were talking about had 36 solar masses and 29, and it resulted in 3 solar masses going off in gravitational waves. That's a hell of a lot. And there's a nice little thing which I put in here, and we talked about last night at supper, but I'll say it again. To get a feel for this field, and how strange it is. Suppose you take that pair of black holes that you just saw in the computer simulation, and we saw for real in the data, and put it not 1 billion years away, but put it at the place where the sun is, 8 minutes away. And what would you experience? Well, it turns out not much. The strain you would get right here in this room would be 10 to the minus 6. In other words, you might be 2 meters tall, you might change by 2 microns. You wouldn't even feel it. You'd feel nothing. But you might hear it in your ear. Your ears are quite sensitive to small motions. Now, but the thing that's sort of unbelievable is this number right there. 10 to the 25 watts per meter squared went through your body when that happened. Now, what does the sun normally put out? It puts out 1 kilowatt per meter squared. That's what gives you a sunburn. So this is 10 to the 22 times stronger than anything that man has ever experienced in terms of power. Well, not quite true. I mean, atomic bombs, but still nothing compared to that. So what it's telling you is it's enormously difficult to squeeze and stretch space. Very, very hard to do. And nature has just about barely able to do it. And it takes an enormous amount of energy to do it. Okay, I think I'm going to skip this because I'm going to get into trouble. Here's sort of the number of black holes. This is just a pretty picture of black hole masses, and these were black holes that people had seen by X-ray studies. Here are the ones we've seen. Their size, this is the mass, and then there's nothing special about the x-axis here. These are all the guys we've seen. Okay, now comes a very interesting new source that we saw last August. And that is a source which was very much like the Hulse-Taylor thing, that thing that first made the discovery of gravitational waves. It turns out it's a completely different thing. It's not black holes. And now I'll let you listen to this. This is that same projection in the frequency plane. Now it lasts for, well, this is from here, 10 seconds is about this distance. 10 seconds, not fractions of a second. And it goes from about 50 hertz, and then it runs out of, we don't hear it anymore, but there is this waveform. This is the frequency dependence of it. And let me play it for you. okay? That's a real chirp, no fooling around chirp. And that's what these two neutron stars do. And when Hulson-Taylor's object, take about 100 million years before that happens, finally get to the point where they have lost enough gravitational energy so they smash into each other, you'll see that system go. But there was a remarkable thing that happened along with that event. And that was, it wasn't just seen by us. And what was seen, that's what's up here. It was seen by a gamma ray telescope. And so the timing is the same. Here's the end of the burst, right there, that we saw. And then here is a burst that was seen by a gamma ray telescope, the Fermi, and about 2 seconds after. And this, by the way, we know everything about this source. It's 40 million light years away. And once we know that, and we have a delay time of only 2 seconds between the gamma ray and the gravitational wave burst, that's where I get that idea that gravitational waves go at the velocity of light. That's where it comes from. And probably you can explain that 2 seconds because of the work that went on inside the source. And it was also seen by another spacecraft. And it was also seen, here's sort of a beautiful picture. It was seen by that Italian detector. In a way, it wasn't seen, but the inference was made that it could have been seen by that detector, and it wasn't. That told us where it was. So here is the uncertainty. Yeah, here's the uncertainty of what LIGO would have had on the sky. This is a picture of the sky, and this big banana thing is this, when you have only 2 detectors, how well can you tell where it is in the sky? And here is the other part of that sky. But the fact that there was another detector in the world that could have seen it and didn't allowed us to tell us where it is, it's at least in this region. And lo and behold, here's sort of the uncertainty circle for that gamma ray telescope. And people began looking very shortly after we made the publication. That was within hours. And they began looking, and they found something spectacular. They looked in this region right there, and they had looked there before. Here's a picture of a galaxy called NGC 4493. That's not important. The important part is the picture of the galaxy. These are stars in our own galaxy, but this is a picture of a galaxy 40 million light years away. And you'll notice that right after this happened, there's a new little dot right there. In other words, when the neutron stars hit each other, there was a huge explosion, and that's called a kilonova. And I think I'll just want to show you this because I'm going to get into trouble with time. This is what it is, a picture of, and people, tomorrow there's a talk at University of Helsinki. If you're really interested in this, somebody can talk only about this kilonova. I'm not going to make a big fuss because I don't have the time for it. But what it is these 2 neutron stars smashing into each other, and as they smash into each other, they make the gamma ray burst a little off axis, and they make these gravitational waves. And so now all of a sudden, everybody has seen this. A lot of people from the ground, people put their telescopes and looked at it. And they saw this. A lot of contributions were made by many, many, many different astronomers. And they uncovered this incredible object, and it became what's called multi-messenger astronomy. So I'm not going to do this. Let me show you where we're heading, and because I have 1 or 2 minutes left. And that is, these are the curves now. I want to just show you why this is for me more than for you. It's just to remind me of what to tell you. But this is, again, strain, and this is the frequency, and here's 100 hertz. And this is the noise curve of advanced LIGO, the real noise curve. And I want to show you 2 things in this picture. We are not at sensitivity. That picture I showed you with the initial detector, we were on sensitivity. Here's the design curve. Here's the design curve itself for advanced LIGO. And you notice there's a big difference still between where we are and what we have, and it extends all the way down. So we are not yet at design. That means there are noises we don't understand, but there are ideas that people have for building better detectors, and I won't go into what they all are. And down here are ideas that both are having, people in Europe have ideas of what to do to really get into much deeper gravitational wave sensitivities so you could explore the whole universe in gravitational waves. And very serious thought is going into that. Here's predictions for a system that might be built in Europe, a triangle underground. And here's a thing which might be built in the United States. This is now many years off, which is 40 kilometers big. And will have the sensitivity. You can see that huge factor of improvement. And, but this picture is just to show you something, why we want more detectors. And here is the thing if you have on Hanford, which is Hanford and Livingston, don't worry about that second one, and the Virgo project, which is the Italian one. And this is sort of what the noise, how well you can determine something on the sky. And that's why let me give you a feel for it. These bananas are sort of the uncertainty in finding something if you happen to be in these locations in the sky. And if you add to this now LIGO India, this is what it looks like. And for example, this is sort of the size of the moon. Now, telling an astronomer, go look at something the size of a moon, is still sort of an insult to most astronomers. They want to know a lot better than that, but that's the best we're going to do. And they're going to have to be satisfied. And they will figure out ways to do it. So, okay, here then is the last slide. And I want to tell you what is going to happen in the field in the next, just in the future. And what it is that this is now a plot of frequency down here, goes to very, very low frequencies, periods of once every universe time, and you can do it up here, age of the universe, this is in periods up here. And see these different ideas. Here's LIGO and all the ground-based things, and they're fairly high frequency. A thing that's going to happen in Europe, with some help from the Americans, is to put a triangle of detectors in space, and it's called LISA, the Laser Interferometer Space Antenna, and that'll have other things it looks at lower frequencies, periods of hours to minutes. And it's a very interesting project, because it'll look at things like the big black hole in the center of our galaxy. When it eats something, we will see it. You can't see these low frequency things with the thing on the ground. Here's a project that's now going right now, which is a project that will look at pulsars, these things I showed you earlier, these oscillating, spinning stars. You can use them as gravity wave detectors. How? What happens if a gravitational wave comes through our galaxy, and you look at pulsars in the northern part of the sky, and you look at the southern part of the sky, they'll go a little faster as the gravitational wave goes through. And the ones on the east and the west, they go a little slower. So by timing the pulsars that you already know, you can see if a gravitational wave has come through our own galaxy. And that looks at other things, gigantic black holes, and maybe a primeval background. And then there's an experiment that's going on right now that looks at the cosmic background and the polarization of that as a way of looking at the very earliest moment in the universe, at the time when the universe was born. And I don't want to go into that. If you ask me questions about it, there's a long story associated with that. So that's the future. Thank you.
Okay, now it's time to ask questions. I'm sure that there are many, but before you start asking the question, wait that you will get the mic, because we have 2 mics here which will be transported to you. So, questions, please.
Yes, hey, what's the wavelengths of those waves that you found?
Okay. Well, it's going at the velocity of light, and the periods you saw are sort of around 100 hertz. So 10 to the minus 2 seconds, and going at the velocity of light, which is 3 times 10 to the 10 centimeters per second, or 3 times 10 to the 8 meters per second. So it has a wavelength of 10 to the 8 meters, about. A very, very long wavelength. Okay? Yeah.
If those gravitational wave sensors are
I don't, where are you, just so I can see you?
If those big machines are built, what else can they be used for?
Well, that's an interesting question and hard to answer. It's going to do science. And what it'll do is the following. I mean, you can anticipate some of the science that those other machines, or even the current machine as it's improved. It becomes, look, we're just at the beginning of an interesting new science. The new science is looking at the universe with this technique of using gravitational waves. And what's so special about gravitational waves? That's the question. What's so special about them is they go right through everything. They don't get stopped. You can't look into the sun with light. You can only look in maybe a couple of 100 meters or so. Why? Because you get blinded, and all the charged particles, they scatter everything. These waves do not scatter. So, for example, if you want to know what's going on inside of a stellar explosion, like a supernova, you will get waves from what's actually going on inside that star as it falls apart. And you'll see, is it 2 stars? Does it break up? Does it form a black hole? You learn a whole new thing you never knew about. You knew about supernova, but you didn't know how they worked. The other thing is we still don't know where the black holes come from. The black holes, for example, ones that we'd love to know, were they born at the very beginning of the universe? Or are they all the result of a star that has collapsed? Or are they maybe the result of places in that we have things in our own galaxy, for example, where there are millions of, not millions, 10 to the 9, billions of stars, all living together, and maybe they come from those what are called globular clusters. We love to know when were they made. How do they get made, the black holes? We don't have the first idea. We have some theories about it. We would love to do cosmology. In other words, we like to measure the universe in a different way, and that's one of the slides I left out, was we have now, by this technique of using the neutron stars, you can now measure by completely different techniques the expansion of the universe. The techniques that don't depend on a lot of things that are somewhat woolly in terms of doing the measurement of the expansion of the universe as a function of distance. So we have an example of that, and that will be done over and over again. We're going to have a different way of looking at the universe. And lastly, because I have to say this, we're going to hopefully find things we haven't thought of. And that's been sort of the history of astronomy over and over again. Every time you change the wavelength. Look, when you look at the universe with your eyes, it doesn't look very spectacular. It's beautiful, but it doesn't look like much is happening. Everything's going very, very slowly. As soon as people turned on radio astronomy, they realized there was hell breaking loose out there. You saw the goddamnedest explosions. You saw jets flying out of places you never would have imagined. Then X-ray astronomy added to that. And then every time we've opened another channel in looking at the universe, you find something new out. It'd be most remarkable if this thing, which is really completely different, would not find some sources that we haven't even thought about. Now, I haven't answered what you wanted. You want to know what practical applications. I don't think it has many. Except, for example, the technology we develop. And if there are people here who have trouble with their microscopes or keeping things stable or understanding how to use light in a new way, they might benefit from the technology we had to develop. But I don't want to make a case that this is a better refrigerator or going to make everybody healthy. It's just not going to do that. Yeah.
Okay, thanks. We're going to take one from the remote audience in between.
Yeah, this is a question from the webcast. How do you synchronize the different detectors? Do you use atomic clocks?
Yeah, the question is, how do we synchronize? And in fact, this becomes more and more important as you get more and more of them. That's a good question, by the way, because it's not a trivial question. And not that the others were trivial. It's just that this is not an easy thing to do. You have to do just what you say. You have to, first of all, you use GPS. But by the way, GPS is another piece of Einstein's necessary to make GPS work. I wonder how many of you knew that. A few of you. You wouldn't be in this room if you had used GPS. You'd be probably several miles off if it was Newton who had this designated how the clocks work. So you had to use Einstein to get that right. And it turns out that that fact that clocks are a function of gravitational potential and change, you have to do something tricky. You have to take, and you mentioned it, the way we got the Livingston site and the Hanford site so they were synchronized is we actually carried a cesium clock, an atomic clock, from one to the other. And they will have to do this, they synchronize all the clocks that are part of the network. And why is it so important? I'll tell you why. The timing is the only way we can determine where the thing is in the sky. We don't see anything. And so, for example, why we knew that this source, the first one we saw, we knew that it was coming from the south. That's all we knew. Why? Because it hit Louisiana first and hit Hanford 7 milliseconds later. And that business is the way you will determine the position in the sky. We can't point these things, you see.
Okay. Okay, I'm going to take one from the back row.
Thanks. Hello. You mentioned there is about a 2-second delay between the gravitational waves hitting and the gamma ray burst hitting. So why is that delay? Because at least in the animation it seemed that the gravitational waves are being emitted at the very last moments of the merger.
Yeah, I mean, look, all we have right now, we don't have a good model yet of I'll tell you something that's very difficult. I'll answer you in two ways. And most likely, that 1.7 seconds, which is that difference. The gamma ray burst came 1.7 seconds after the moment at which the two neutron stars bashed into each other, okay? So that we know, but we didn't see the final bashing. Why? Because that's at a kilohertz. That's where the frequency, the millisecond. And why? Because our detector is not very sensitive at that frequency. So we didn't see it, but you can infer where that is. Now, many people have now modeled and are starting to model what goes on in that collision, and they think that it's not unreasonable that there should be a delay of about easily between 1 and 2 seconds between the electromagnetic display and the actual gravitational wave collision that measures the accelerations. That 2 seconds, but when I gave you that number of 10 to the minus 15, it knew that's where that 10 to the minus 15 came from. I say 2 seconds in 40 million years, and you do that number, and that is 10 to the minus 15. Okay? Did I answer what you wanted?
Yes, thanks.
Yeah, okay.
More questions? No, from this side?
So I have basically 2 questions, but I will maybe start by the first one. In that slide that you showed with the interferometer and the 4 test masses, 2 test masses in each arm. So basically, if you said that they have some transmittance, let's say it passes 1 time in every 300 times it hits the inside mirror. So how do you make sure that both mirrors in each of the arms have exactly the same average transmittance?
That's easy.
Or do you put the distance between the 2 test masses in each arm at the exact wavelength, so you are sure that they are in phase when they get out of there?
Yeah. Let me see if I interpret your question. You're asking the question, how do we establish that since we want no light at the photodetector, how do we establish these things that are 4 kilometers on an arm? How do we establish that they are indeed exactly equal times in both arms? That's the question you're asking.
Exactly.
That's a very easy thing to do. I'll tell you why. What you do is you deliberately put some modulation. You do something to the light that comes into the interferometer. You give it a waveform of its own at a different frequency that you know. And if it turns out that you see that modulation, let's say the light is at 10 to the 14 hertz, and you modulate it at a megahertz, okay? You make an envelope modulation on the light. And so a megahertz, and you look for that megahertz signal at the detector. And what you do is you set the lengths equal by making that 10 megahertz signal disappear at the detector. That's the way you do it. And because that's the only time you know that if you're insensitive to frequency modulation of the light, you have equal paths. That's one way to, once you do the algebra, you'll see. So it's fairly easy to establish if you have gotten the interferometer at the equal time point. That's not hard to do. Yeah.
And the second is also probably easy, but how do you establish what is the initial mass of the bodies and what is the distance they were?
That's a good question.
Because from my understanding, you could know the initial position and use it in the calculation, or you know the initial masses. So.
Let me be fast with you about this. Remember, the whole trick to being able to measure 10 to the minus 18 meters is by using servo systems everywhere. And what we do is we actually take out, for example, one of the things that's huge is the tides, the earth tide. The earth tide is about 10 to the minus 7, it's a strain of 10 to the minus 7. So it's a 10 to the minus 7 times 4 times 10 to the 5. So it's 4 times 10 to the minus 2 centimeters. It's huge. That's the earth tide, but it's at a frequency of once every 6 hours or 12 hours. And we take that out by actually moving the masses so that you always stay at equal separation. See, we don't look at that frequency. There are many things we do to always keep the thing so it's tuned up. And that's why we have given up on looking at very low frequencies, because the noise is so terribly big. So if you look at those curves, all of them diverge. They get terrible by the time you get to frequencies of the order of about 10 hertz and lower. And none of these detectors are going to work at low frequencies. And that's the reason why people want to put a thing in space. Okay? In space, you have a different problem. You now have to keep these things in orbit in such a way that they stay with velocities that are small enough so they can talk to each other. But it's always a relative motion that's important, not an absolute motion. Okay? Think about it. All right, come and talk to me. I'll draw you pictures. Yeah.
All right, so you mentioned that a few solar masses of energy go into these waves, and also that the waves don't really interact with anything. So is there any way to get that energy out of the waves afterwards, or is it like lost?
Yeah. It's pretty much lost. Let me tell you, I'll tell you why. And people who would dearly love to do something about that energy are people who have dreamt about taking and harnessing a black hole. I'll give you the standard sort of perpetual motion kind of idea that people have. And that is, the gravitational waves are a crummy way to collect the energy. A much better way to do it is find those black holes and bring them here, put them somewhere in orbit around us, and start putting a little lever system with a pulley and drop things into the black hole and use that energy as the thing goes in the black hole to drive generators. And that, yeah, you're welcome to do it, and it's certainly going to work. But I don't know, you got to be very careful. I mean, that's way off. But I'll tell you, the people who are thinking of applications of gravitational waves are the nuts. And many of them are military nuts. I'll give you the military nuts. We talked about this, I think, with somebody here. The people who have got plans for this are the people who are trying to... Yeah, first of all, let me say, you can't do anything with the waves because the fact is that to harness them, the amount of motion that you're getting is so small, even for these enormous powers. That's why I told you about that little calculation of putting this thing at the sun. Look at the power that you need, and you get nothing for it. That's the real problem. And that's because gravitational waves just don't interact much with anything. But there are people who think, well, maybe you should use gravitational waves to communicate. And that's an idea that some of the military in China thinks is useful, and some military in the United States thinks is useful, and it's complete nonsense. And they are fighting with each other who will first develop a communication system that works on gravitational waves. Why? Because then they can communicate with the atomic submarines. Now they can't do that in a nice way because they're stuck with that highly conductive water that the submarines live in. And they would love to be able to tell a submarine launch or not launch. Okay? So it's complete nonsense. It's fables and they're egging each other on. The Chinese are telling their government, yes, the Americans have a way of doing it, and the Americans, the ones who are pushing this, are saying, yeah, the Chinese have a way of doing it. So idiot money is going into this. It's complete nonsense. Okay. Yeah.
We're going to take one from remote.
Yeah.
Okay,
audience.
we have another webcast question. It builds on the last question. If gravitational waves do not interact with anything, what happens if two gravitational waves collide? Would they resonate or interact as normal waves do?
Yeah. Well, okay. That's a hard question because it's a question that you can answer theoretically if the gravitational waves are strong enough. And so far we haven't encountered any, and we've looked at some pretty energetic things. But suppose there are some gravitational waves that are really huge. They will interact with each other. Why? Because they both affect the geometry of space. So yes, but in any practical sense, they do not interact. Okay? I think that I can't give you, I don't want to say there's no way it's possible. But yes, if they are strong enough, they will. But we don't know of any source, even these black holes. Look at it. They just don't do much. And it's because of this problem that you can't squeeze space. It just takes too much energy to do it. So yes, they will interact, but it's of no consequence. Yeah.
Okay, we are taking one last question from the audience now. That hand was up very early, so.
So my question is a bit speculative.
Where are they? Okay. Yeah.
My question is a bit speculative. So using these detectors, will we be able to make some observations of the universe from the times before the light decoupled from matter?
Yeah, that's a very good question, and people are hoping that. What he's asking is, and can I embroider your question a little bit? Okay. What you're saying is, with this thing that is so penetrating, these gravitational waves which don't get stopped by anything, one does contemplate, could one look all the way back to the moment that the universe got generated? And a lot of people have given a lot of thought to that. And it turns out that this B-mode experiment that I gladly described to you, but is trying to do that. It's trying to look at, well, maybe I quickly should say what it's trying to do. It's trying to measure properties of the electric polarization of the cosmic background that are due to density fluctuations that happened in the plasma of the early universe. And that plasma has been excited to density changes due to gravitational waves that were generated at the instant when the universe was created. way before before this. And so this is a fundamental measurement, but it's not a direct measurement of the gravitational waves from the moment of inflation. It's a way of indirectly measuring it. It's a very wonderful idea, and I hope they succeed. It'll be a masterful experiment, better than LIGO even, far more impressive than LIGO. So it turns out people are working on that. But now the question, let me try to answer your question another way. There are people who are trying to think of what kind of an instrument you might have to make so that you could actually directly detect the gravitational waves that come from that instant of the formation of the universe. And there's something you can look up on the web if you want to. It's called the Big Bang Observer. Big Bang, that's the cosmic initial. Observer, that's the name. And if you'll find, go to Google and you'll find lots of stuff on it. It's an idea that people thought about probably 5 years ago, 6 years ago. It's so complicated and so difficult to do that LISA has to be done first. And once you have LISA, which is that thing that is now going on, when that succeeds, it may be possible to begin to think about this experiment. I'll tell you what it means. It means taking all the complexity of LIGO and all the high-power lasers and all the servo systems and putting them into space. And that nobody is willing to contemplate that yet. LISA is extremely primitive compared to LIGO, even though it's done in space. Thank God, because it'll succeed, I think. Yeah. But there are people thinking about building a special purpose gravitational wave detector. You will do it in space with the big distances you can get, and to look specifically for that radiation. And I'll tell you what will push that. If the people doing the B modes actually see something, the people who do all those early experiments they're doing now, if they see something, there'll be tremendous pressure from people doing cosmology to try to see what is the spectrum of that radiation. But that'll be in not my lifetime, maybe in yours.
Okay, so let's thank Rainer Weiss again.
Yeah. Yes, thank you. Yeah. Thank you. Okay.
And now everybody is welcome to the reception outside the auditorium, and you can continue asking questions from there.
I'm hanging up, hanging around. I'll answer anything, and you'll find out how shallow my answers are presently.